This is the OR gate. All right, again, this is also an active high gate. All right, well, we've got our two inputs. We've got A and B, and again, we have four combinations, four possibilities. We have A is high, B is high. Oops, B is high. Well, an OR gate works if either A is high or B is high. So if I look at this and I can ask myself, is at least one of these gates, is either of them high? In this case, yeah, both of them are, so it meets the criteria. At least one of the gates is high, so my output is high. Well, here's another one. So maybe only A is high and B is low. Well, ask again. Is at least one of these gates high? Is A high or B high? In this case, A is high, so it meets the criteria. So it outputs a high signal again. Or we have this. We can reverse it. A is now low, but B is high. So again, at least one of the gates is high. So the output is high. And then we have our last condition where both are low. And in this case, it is not true that either A is high or B is high. In fact, neither A or B is high, so the OR gate will not output a signal, or it will output a 0-volt signal. All right. Now, you might look at this and think, well, this seems kind of like this seems to make sense, but what if I really only want it to respond if one or the other is high? So maybe I want these two cases to return a high signal, but I don't want it to return a high signal in this case where both of them are high. I really, really want to know if only one of those signals is high. Well, fortunately, there's a gate for that. That gate is called the XOR gate. Okay, that stands for exclusive OR gate. So we have our four possibilities: high, 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 low, low, high, and low, low. Now, these two cases meet the criteria, so at least one gate is high. And now, the exclusive OR gate will get rid of this situation so that it only responds if these two cases happen. And then just like the other one, this one is still going to return a low signal.